we've spent our first little while talking about the role of multi-phase fluid flow, I guess, in systems. So we dealt with D NAPLs and L NAPLs, talked about them as being the source zones that they get into after maybe a month, and then they stick there, tough to get out because they're held by capillary forces, so they're quite stubborn. They can move, and we understand the behavior of relative permeabilities and multi-phase flow, but largely they will stick there and act as a source. That source is important because water flowing through it, even though these compounds are only very mildly soluble, they do dissolve, and they are a problem at really super low concentrations. And so their transport from that zone by advection and diffusion is important, and we talked about some models to be able, or methods to be able to understand both the physical processes, diffusion and mechanical dispersion, and advective transport in moving them from upstream to downstream. You know that they dissolve slowly, and so they're quite persistent, and so if you don't remove the source, then for remediation methods, you don't really solve your problem, but you just deal with the consequences kind of in perpetuity, like pump and treat. And so we know that from what we understand. We talked about how the concentrations and the rates at which they move downstream might be conditioned by the fact that retardation and attenuation occurs, by sorption onto mainly organic carbon, but also onto the substrate surfaces of the grains that we have as we're going downstream. And sometimes these source zones will be in the vadose zone rather than the groundwater zone, in which case the most effective way for it to end up in groundwater would be for it to be washed in by rainfall percolating down to the groundwater table. So that's what we've covered, everything in terms of physical processes. So that kind of will inform the kinds of questions that you would ask when you're doing remediation as to how these methods work. Do they take the source away? If they do, how do we do that? If it's held by interfacial tension, we could heat it up and it would vaporize. We could try and wash it out, not going to be very useful. We could use surfactants to reduce surface tension, and that would mobilize some of it. We wouldn't want it to get in the groundwater zone. If it did get in the groundwater zone, how would we remove it? I guess by doing things like pump and treat, and we know how that's conditioned by things like permeability of the aquifer, etc. So that's kind of the physical background of what we've had so far. So what I want to talk about today is how we might represent these processes of mass transport, flow and mass transport, when we have something that's a bit more complicated than this linear core geometry, for which we have some models in here, and for these flat plume geometries that we talked about for migration with the Gaussian distribution. And so we'll just touch on mathematical models today. And then after that, on Thursday and on the following Tuesday and Thursday, 1 week after you get back, then we'll talk about how methods of being able to figure out what the properties are of aquifers that allow you to quantify these things, the kinds of things that you've been given in your assignment but have to come from somewhere. And so how would we actually get that information in the first place? So that's what we plan to do today. So we'll talk about mathematical models, very simplistically as a conceptual level. Talk quickly about an example just to kind of frame it potentially, and then talk about finite difference methods for flow and advection. Do you see this in your past, in your math classes? Finite difference methods, solving PDEs? No? Finite difference not mean anything? Huh?
I know what finite difference.
Yeah, fine. Yeah, finite difference as in dp dt, delta p, yeah, fine. Okay, fine. So we don't presuppose any background in this. Oh, some background. I'm just curious what you see in your background. So in terms of a case study, so this is kind of the process. This happens to be a waste site in New Jersey, apparently. It was a former landfill where a bunch of stuff was dumped and was migrating from the site. And the question is, how quickly and in what concentrations does it move downstream? And you could use this kind of Gaussian distribution model that kind of flattens and widens as it goes downstream to represent this. You have a source, which is here, which is a continuous source, so it would be kind of amenable to that. But another way would be to represent the real geology and permeability distribution and characteristics of the site in its own way, its own heterogeneity, and to try and come up with a solution based on that. And so the steps to do that are to realize exactly what your site looks like. You have, you have something buried in the ground, which is the source. You have a number of wells which would have taken samples. Clearly one well would have turned up a sample that was questionable, which would direct you to wondering what the hell is going on here, and to look upstream. And then more drilling would actually confirm exactly what the state of the situation was in terms of this source. So you'd have these pockmarked well bores which should say something about the plume. And if you wanted to deal with that, what you could do is you could make a model which would divide your plan view up into a series of elements. And these elements would be exactly where you're looking at mass rate in equals mass rate out, and the change is any accumulation. They could be little cubes or they could be triangles. They're just written slightly differently, but it's the same thing. Each of these finite elements would account for the amount of fluid that came in through one face and the amount going out through the other faces or sides, and do the accounting to be able to solve a big system of linear equations to do that. And so you'd set up a model to do that, of which there are many available. You would want to calibrate that model so that it actually returns the behavior you have. And of course the behavior you have would be by looking at these individual boreholes, which would have, for instance, water pressures or water levels in them, which you could then draw a section through. And on that section you could plot how the water levels change as you go downstream. Flow obviously would be in this direction as you go from high head to low head along the section. You'd expect maybe that there's some heterogeneity in here, that you have this kink in the water table or something going on. And you run your model forwards so that when you run this model with some boundary conditions defined at the edges of this model, upstream, downstream, sides of the model, so that when you run it with those boundary conditions, you actually replicate the distribution of heads along some section. And if you replicated the distribution of heads, you think you perhaps might have the right pressure profile upstream and permeability magnitude distribution. And so then you can recreate throughout the aquifer your flow regime. And so you've done this actually, right? You've done a little question like this on the BTEX one, where you had to decide which is the direction in which transport would occur, and you do it by drawing the contours, and you know that flow would occur in the direction of maximum flow velocity, which has to be perpendicular to the contours of equipotentials. So you do that, and then you perhaps do something like put a well in, start sucking water out. That will change the head distribution. You can imagine this being a contour map where you have a depression here, a cone of depression, a valley, which everything is flowing into from the sides. Flow occurs perpendicular to the equipotentials, so it will be brought in for all sides. And the idea is that you pump it out here, you capture the contaminant that is being driven down from upstream, and then you remove it. And so the first layer is to do the flow problem, which this really is, right? Apart from these arrows here. So you know what the change in the groundwater flow would be. And then you superimpose on that the velocity structure, which you can get from these equipotentials, and use that to calculate what the transport would be. So you put something in a location, you allow your model to run to see what the plume would look like in 5 years to get to where it is now. So you have some confidence because you can measure these magnitudes of the concentrations in the well bores that you sample from. And then maybe you turn on a pumping well to be able to capture this and suck it in. And so that pumping well would allow you to capture it so that over time you'd actually reduce the concentration in the plume and it would disappear over time until there's nothing there. So that's the basic idea. And perhaps you might want to go and take out the source as well. So that's the kind of things that we might want to do. And the question is, how in a tangible way can we do that? And so we'll just talk about models that represent our system. So we know that we've had two systems. We've had a flow system. The most complicated one was with multiple fluids, but if we take away the two fluids and just do it for a single fluid, then our flow equation is just this. Hydraulic conductivity, second order partial of head with X, second order partial of head with Y, mass in equals minus mass out equals accumulation. This is a storage term, storage coefficient, and a change in head as a function of time is how the storage of water is manifest. If you want to cram more water into a given volume, you have to increase the pressure by pushing it in there, and that is manifest as a change in head elevation, which is proportional to the pressure. So there's a flow equation that we want to define, which we broadly define as this, and it comes just from a continuity equation. And on top of that, there's the transport equation, which defines the motion of the contaminants as they get carried downstream. And it gets carried downstream by advection, according to the advective velocity, and also by dispersion, both longitudinally and transverse, for a two-dimensional problem. So typically for a two-dimensional problem, we've thought about it in the z is vertical, so x and y are horizontal. X would be the direction of the maximum velocity if we're using this kind of formulation. And this would be the accumulation term, including retardation and attenuation in the retardation coefficient. So if we want to do exactly what we did before, we want to solve the flow system first, calibrate it, and then run it to reach our current conditions, and then keep on going to model what it would be in 5 years' time. And then with that model, we stuck on top of the back of it the transport behavior to try and see how the contaminant plume would evolve over the same time. And so that's kind of the sequence of events. We've talked about it in this simplistic mode of traveling downstream in a core. And so that's probably the most convenient way for us to look at finite differences in representing this behavior. And so we'll look at how we would represent those equations. So what we can do is we can take just a linear core. We have an upstream node, a downstream node, and an intermediate node. And if we simplify this equation, if we throw away the storage term, so it's steady state, and if we think that we only have one-dimensional flow in this simple core, then the appropriate equation would be that this equals 0. If this equals 0, it actually doesn't matter what the value of the hydraulic conductivity is. We can throw that away as well. And if this is equal to 0, we don't care what the value of k is. It's not going to modulate it in any way. And what we would like to do is to be able to solve this partial differential equation. So what we can think of is this core as being these three nodes. So we think of these three nodes as a template between an upstream node, a downstream node, and a middle node, where we want to calculate what the head is at this middle node. And if we draw a cross-section through those three nodes, ignore the ones up and below for the moment. Actually, why don't I just take them out so you don't have to think about them. You can always replace them. So we're dealing with it in 1D right now. So if we drew a section through along this core, then the upstream head would be the head at node 3, the node in the middle would be the head at node 0, and the downstream would be the head at node 1. And this would be just like our calibration picture through our aquifer, except just written for these three individual nodes. And then from those, if we look at the elevations of these, this would be the finite, the head differential, delta H, and this would be a different head differential, delta H. This would be 0 to 3, and this would be 0 to 1, or perhaps 1 to 0. Right? Just the head differences. And so these define these as partial differentials. So this could be 1 over delta x, this term here, multiplied by delta h over delta x. That's all we're doing. So we're writing this second order partial differential as to what it is by splitting it out in longhand, identifying each of these components as finite derivatives, not partial derivatives, and then trying to figure out exactly what these are. So we can take this portion first. So if we want to get the change in head with length, we can do it on this portion here. So dh1 over dx would be the head change over the length. So it would be the head change between this node and this node, which is just this. All is written in the convention from upstream minus downstream, so we can get our gradients in the right order. And the head differential over this part is going to be the difference between the head at node 0 minus the head at node 3, divided by the length of which it occurs. So these are just the finite derivatives. This represents the delta h over delta x over this length, and this represents delta h over delta x over this range. So we can get those individually, and we know from the two slopes of this, these have to be different values, right? If they were the same inclination, these would both be the same. If one is steeper than the other, this would be larger than this one in this particular case. So we can think of these values here as written right in the middle of these two delta x segments. And so the definition of this term here, d dx, is how the gradient changes over this length delta x. And so this length delta x now becomes the difference between these. So this also, this length here, would be delta x. Right? So we have a value of dh dx at this point, we have a value of dh dx at this point, and they're separated by some length. So this is how this value changes as we go over this length. And so this term here would just be this term here, which is here. This term here, which is here, and divided over the length over which those occur. It's exactly the same as we did for the, we happened to work with heads before, upstream and downstream. Now we're working at changes of heads with length, upstream and downstream. That's all we're doing. So we've done that a second time. So if we do that, and we take this long expression and we simplify it, we'll end up with h1 minus h0, these two terms here. I won't do that. Minus h0 minus h3, so minus h0, well, I don't want to confuse things by doing this, but hey, why not? So this term here would be this, right? That makes it more apparent. So h1 minus h0 goes here, h0 minus h3 goes here. This is minus. If you take the brackets away, then all of a sudden this one here becomes a plus, right? A minus minus a minus. And so if you gather those terms together, then you get h1 plus h3 minus 2 times h0. You have the delta x over delta x, so that's delta x squared, and it's equal 0. And so that's the only derivation we need to do. And so what we realize is that so long as the middle, this is a constant, so h1 plus h3 minus 2h0 has to equal 0. So basically all that is saying, if you add the two n-member terms together and divide them by 2, that should be the value of the middle term. And that's what that's saying. So what we could do is we could iteratively go through this system and go first to this central node, not knowing what the head is, but if we knew what the head was upstream and downstream, we could add those two together, divide it by 2, and replace this value at the central point. And then we could go to the next node and look at its surrounding values, add them together, divide by 2, and replace that value by that value. And that's exactly what we're going to do. So it turns out that if we look at a one-dimensional problem that we just had, then our system looks like this. Then the value of the head at the middle node is equal to upstream and downstream added together divided by 2, just their average, and replaced there. If we look at 2D and we add this extra term here and treat it exactly as we did for this previous one, then the template that represents that system is now in 2D. It has upstream, downstream, and if you like, cross-stream. That's why we label this 3 and 1 before. They might have different values of x's and y's, but if we choose them to be the same x's distance, so in other words, we just have a grid which is the same lattice separation in x and y, so it's just a square grid, then the central node is just equal to the bounding nodes, 1, 2, 3, 4, added together and divided by 4. So again, it's just an average. And if we wanted to solve the problem in 3D, so 3D would be, this term here would be plus d2h dz squared, right? Would go in right up here. I'm not going to redraw that, but this would get added in there. And again, the template would look like the square template we had, but with z added on for h5 and h6. And not surprisingly, no, that's wrong. Pretty sure that's 6. For the same reasons before. So again, it's just the average of all of these surrounding nodes divided by 6. Well, that is the average. It's the sum of all these surrounding nodes divided by 6, which gives you the value of h0. So since we know that that is the rule, we can define a kind of method to do this pretty straightforwardly. And so the straightforward method is to take this core that we had before, which is kind of our aquifer. Instead of having just an upstream and a downstream node and one middle one, why don't we put 2 mid nodes in between the upstream and downstream? And then we can go about by applying this template by putting it over nodes upstream, next one, and next one first, doing something, and then moving it downstream so it covers 1, 2, and D next, right? And so we can set up a little scheme where we take the upstream head, which we'll say is 1 meter. We'll take the downstream head, which we'll say is 0 meters, just to make life easy. We don't know what the heads at these intermediate locations are. That's a mystery because we have to solve for that. But what we could do is we could assume some values. We could either assume 0 to be the same as the downstream, or we could assume 1 to be the same as the upstream. Doesn't really matter which ones we do. And so all I've done here is I've assumed that those heads are equal to 1. So it's the upstream nodes is 1, 1, 1, and 0. And then we go through and apply this template. So we apply the template and we first apply it onto these 3 nodes. So we add 0 plus 1 divide by 2, and you get a half. If we want to get the head at this node, a revised head at this node, so this half replaces this 1. If we want to get the head at this node, what we could do is we could add the head at this node and this node together. That would give us 2. If we divide that by 2, that would give us 1. That's one way to do it. But we've already got a better piece of information for the neighboring head. We could use the updated one directly. So if you use this head, this one, plus this one. Actually, this one isn't going to change because it's a boundary condition. If we use a half plus 1, that's 3 over 2. 3 over 2 divided by 2 is 3 over 4. So this is the new value we substitute here. And then that's our revised value. We want to do another iteration, so we'll go back. We could start at this one, or we could start this one. Let's go to this one. So if we want to get the revised value of this head, 3/4 plus 0 divided by 2 is going to be 3/4 over 4 times 2, which is 3 over 8. So this is the revised value here. And now we want to get a revised value for this. So we'll take this value and this one and add them together. So this is 3/8. I guess this would be 8 over 8. So this is 11 over 8. Divided by 2 is 11 over 16. So that's this value. So these represents our next estimate. So now the next one is to get this one. So we'll take 0 plus 11 over 16 divided by 2 is 11 over 32. We'd take 1, which is 32 over 32 plus 11 over 32, which is 43 over 64. 43 over 32 divided by 2, which is 43 over 64. And then it's getting boring. We take 11 over 32. No, I guess what do we do? Yeah. We take 11 over 32 plus 43 over 64. So that would be 22 over 64 plus 43, which should be 65. Okay. That's, oh no, that's right. What have I done wrong? Okay, to get this, take this plus this and add them together and divide by 2. So this plus 0 is 43 over 64, divided by 2 is 128, okay? And now to get this value, I take 11 over 32, which is 22 over 60. No, I don't. So to get this, I take this, I divide it by 2 to get something over 256. So I guess this is 256 over 256 plus 86 over 256. Does that give us 171? Anyway, so if I check, if I can, does this come up? 171 over 256. Those numbers should each be asymptoting to 0.6, 0.33. So if it's a linear gradient, it's going to be 1, 0.66, 0.33, and 0 at the downstream. So 171 over 256 is 0.6679, which is pretty close to what we want. And 43 over 128, if you can see it, is 0.335 something, right? So basically they're asymptoting to be the values that they want to be. So this is almost, whoops, 0.66, and this is almost 0.33. And you can keep on going, but they'll get progressively closer and closer to this. They won't make any big change because they're almost essentially there already. And so now what we have, which is really rather like our section through our site that we had before. We had these water table gradients. As you go from upstream to downstream, the model now represents the in situ hydraulic gradient that you could measure. And so if you apply this model by using a grid, the grid would look just like a lattice square grid in this particular case, that you went individually around every single point, summed up the 4 surrounding nodes, added them together and divided by 4, and replaced the central node, and kept on working through the grid. You'd end up with a distribution of heads that would satisfy those PDEs, that 2-dimensional PDE. So that's what we've basically done. So what that doesn't tell us anything about is it would allow us to simulate how the drawdown looked, but what it wouldn't allow us to say anything about is how the plume would evolve in the system. So we have to overprint the transport equation on top of that and solve that. And so the easiest way of doing that, which is how many codes do it, is by a method that's called particle tracking, for obvious reasons. So now we have the distributions of heads in this system. And the distribution of head would look like this, right? The head is equal to 1 upstream. It's equal to 0 downstream. If it's Darcy's law, it's linear between those points. So this is 0.66 and this is 0.33. So we have the gradient along the length. We also know that the Darcy velocity is given by the hydraulic conductivity times the gradient. So we could calculate what that Darcy velocity was, because we know the gradient here, the head changes here from 1 to 0.66. So this by definition is 0.33 meters. This length, I didn't say it, but this is 1 meter long. So by definition, the gradient is 0.33 over 1 times whatever the hydraulic conductivity is. And so that would give us a Darcy velocity. If we want to get the advective velocity, we divide that Darcy velocity by the porosity. And so that would be, instead of 0.33, it would be 0.033 meters a second. And so we have the advective velocity for that system. So if we wanted to solve the transport equation, we could use this, but we could use a slightly different method by realizing that we want to represent this plug flow behavior. Simplest for us to think about it. And we know that as we go down gradient, the distance the plume will travel as we go in x, and c over c0 would be a length which is equal to, velocity is equal to length over time, so velocity, this would be velocity times time, right? So maybe we can mimic that somehow just by using finite differences again. So we know that the velocity is given by length over time. The length traveled is a distance x in a given time. And so we could get the distance traveled as being the product of velocity times the time step over which we allow that to travel. So you're going down the road at 10 miles an hour, you do it for an hour, you've gone 10 miles. That's all we're saying. And what we could do is we could merely calculate how far we've traveled in a given increment by taking the location where we are at the beginning of the time step, adding a length onto it, which is the length of the time step, where that length would just be given to us by this difference here, just by time stepping. And so what we can do is by using particle tracking, we can merely write this equation. If we know that the distance traveled is going to be the advective velocity, we said that the advective velocity was equal to 0.033 meters a second. We can choose a time step, and that we can know that each of those time steps will go a distance that's given by that. And so all we need to do is we release a particle at this source, at the upstream location, we allow it to go downstream, then we release another particle at the next time step, and we see how they all move downstream. We can calculate within each box or bucket that they arrive from the number of particles what the concentration would be, because each of those particles represents a released mass of contaminant which is sent from the upstream location. And if we do that, we can essentially replicate what these models do. And that's all these models do. That would allow us to be able to calculate the observation at the compliance location in terms of the residence time distribution. But I guess more importantly, we might be interested to see exactly what the plume looks like in terms of seeing exactly in plan view, if you looked at it, exactly what the concentrations would be as you go downstream. So just like Borden, these would be almost zero concentration. The biggest concentration would be closest to the source, and we have a full distribution of those as we get downstream. We're looking at flow only with a velocity in the direction perpendicular to the equipotentials, but what will also happen is you get dispersion that occurs laterally as well as longitudinally. And so we know what these plumes would look like as you go downstream. So it merely allows us to do that. And it turns out that we might want to be mindful of a couple of things, in that we might want to use our concepts of these two non-dimensional numbers that we talked about, the Peclet number and the Courant number, to define how our system behaves. And so a couple of things that come out of this is that Peclet numbers represent how dominant advection is, plug flow, over dispersion. And so if we have plug flow dominant, it would look like this. So this would be a Peclet number, right, of 10 or above, right, we determined. And if Peclet number was much smaller, then it might look like either this, or it might look like this if it's purely diffusive. So this is Peclet number goes to 0, these forms here. So it turns out that if our Peclet number is 0, it's pretty easy for us to solve the transport equation. When the Peclet number becomes large, if we use standard finite difference methods to solve this, the equations typically fall apart. And so we have to regularize it in some way. The method we just talked about in terms of using particle tracking actually tends to be stable at a whole bunch of Peclet numbers, even when this becomes infinite, when this would really be a very sharp front. So that's great. But the other thing that we need to account for in looking at solving in this way is to use a Courant number which allows us to get a good solution. And we always define the Courant number in terms of, well, it's the number of pore volumes. It's equal 1 when the core is completely filled up with water sent from the upstream boundary condition and it's reached the downstream. If we define the Courant number as a velocity times a time step, which is of course a length, so this is the length traveled for one pore volume, this is the length traveled, and if the length of the core is delta x, when this term equals 1, that physically means one pore volume. If instead of defining delta x as the length of the core, we define it as the length of each of the individual elements. So in this particular case, we had an upstream element, an intermediate one, and a downstream. Each were 1 meter long. And if you think about it, if we have a Courant number which is larger than 1 when the length scale is defined as the length of the element, then a particle will enter from the upstream side and it will completely traverse this and leave the element before it knows it's been there. And so if you solve this system with a time step, which gives you a length of transport in each time step, which is bigger than the length of the element, then the element doesn't have any knowledge of the thing passed through. It's already passed through and it's somewhere downstream. So when you solve these systems, you have to choose a time step which is small enough to be able to capture that information. So it means that you can use this to define the maximum time step. So delta t max should be, if this should equal 1, delta t max, if I just rearrange that, should be delta x over advective velocity, and it should be less than that. So if you just rearrange this for that equal 1, this is the length of the element. then you don't want it to have traveled the complete element and come out the other side in a single time step, because you won't have any information on where it's gone. It'll have left the compound if you think of that. And so by using a time step which is small enough to keep all of these individual particles within the single element within every single time step, then you'll get a solution that actually means something. So that's it. That's all that these numerical models do. They take these somewhat complex partial differential equations. They can represent them as finite differences quite easily. Hopefully you can represent what the finite differentials mean in terms of just these head values as you go downstream, both in terms of a first order PDE defined at each of these nodes, and then a second order PDE, which is just the change in the first orders between the upstream and downstream. It turns out to be a very simple expression if you take constant values of hydraulic conductivity and throw away the storage term. And the physical representation of those is that if you take the middle node, that head should just be the average of the upstream and downstream nodes. If you work in 2 dimensions, the middle node should just be the average of all the nodes around it. And if you work in 3 dimensions, it should be the average, again, of all the nodes around it. So these so-called residual methods, they're residual because you merely modify the value of this previous head by marching your way through the grid multiple times, as we just did here in 1 dimension, until you have a solution that doesn't change between the iterations. That gives you the correct distribution of heads. If you know what the distribution of heads are, you can calculate your advective velocities, and you could either use those distributions of advective velocities to solve this equation as a partial differential equation, just like we did here. It turns out that doing that doesn't work very well if the Peclet number is bigger than 10. It falls apart because it's dominated by this first order term, and these methods of solving don't work very well for first order differential equations. However, if it's dominated by this first order term, particle tracking works really well. It's just like tracking a number of cars driving down a road. You know the direction the car's going, you know its velocity, you know how fast it's going, so in a given time step it'll go X meters, and you can just account for those as it goes downstream. And by that you can get a solution that looks like the ones that we looked on the previous page. So if you ever do this stuff, you probably won't make your own codes, but these codes just do exactly what we've said, but in a more sophisticated way. And it's all hidden to you behind the graphical interface and the output, etc. But the things that you do need to know is that you can still garbage in, garbage out, I guess is the computer adage, right? If you don't know what you're doing with the code and you do something like use a time step which is too big that doesn't keep the solution stable, or use a Peclet number, the one way that you can keep the Peclet numbers small is that you could use, again, a grid which is much finer. So typically what you do if you're solving these equations using the PDEs, so in that particular case you work on a distributed grid. I guess I didn't want to do that. You work on a distributed grid that looks like this. So this is your mesh. Our mesh would be squares rather than these triangles. So this is the mesh of which you define the length of the elements. So the length of the elements will be delta x. So if you want to make a solution that you think would be unstable for a large Peclet number stable, is that you reduce the Peclet number. You can reduce the Peclet number. Advective velocity you can't change. Dispersion you can't change, but you can change the size of the element. And so if you halve the element size to have a much denser grid, all of a sudden you've halved your computational Peclet number. Hasn't changed the Peclet number in the field, because the field one is done on some kind of dimension, length dimension that you define for the system. Here we're defining the length dimension according to the mesh, and that will change as you change the mesh. So if you have 10 times more elements in the x direction and make 10 times more in the y direction, your size of elements will be 10 times smaller, and so you'll have reduced the effective numerical Peclet number by a factor of 10, and maybe all of a sudden it's in range to get a solution where it would work well. So two numbers that are important in doing these solutions would be the Peclet number, because models like this don't deal very well with very sharp fronts. They can't represent these very sharp plug flow fronts. And Courant number is important because if you're using a method to represent high Peclet numbers, which is this particle tracking method, the particle as it moves downstream has to reside in the element for a certain amount of time, otherwise it doesn't know it's been through there. And so if it doesn't know it's been through there, it doesn't give you a good solution. So that's it. So I don't expect that you'd ever create these models, but that's exactly how they work. So, are people going to be here on Thursday? Yeah, okay, I will as well then. We'll talk about site investigation. So this is the package that kind of integrates what we might want to do if you know what the parameters of our aquifer are and what our aquifer looks like, how deep it is, how thick it is, what the heads are within the aquifer, etc., what the concentrations might be. We could use the models to be able to project what behavior might be. And so what we'll talk about for the next 3 sessions is how we might get that information by doing site investigation.